Let's talk about the second type of transformations that can take place on things. For previous lesson, we talked about translations or shifts, meaning moving left or right or up and down. Next one, we're going to talk about stretches. And there's two types of stretches. One, which we did last year with parabolas, quadratic functions, which were vertical stretches. So it's stretched up like this from the x-axis, or it compressed and went out wide. Okay? But every time we did a vertical stretch, it's the y values that were affected. The x values stayed the same. So just a quick review from last year. If we sketch y equals x squared, should be pretty familiar with this one right now. 0, 0, 1, 1, negative 1, 1, 2, 4, 2, 4. Almost y equals x squared. If we did 2x squareds, remember we went 0, 0, stayed where it was, but 1, 1 stretched from 1 to 1 times 2, or 2 up. 2, 4, and negative 2, 4, the 4s stretched from 2 to 8. Got it. So y equals 2x squared looks something like this. We saw that the graph of x squared got narrower. So that's y equals 2x. But notice the x values stay the same. Here, the x value is at 1 from x squared. And then here, the x values are still 1, but it's the y values that doubled. And then for a half square, we stuck at 0, 0. Because remember, we're stretching from the x-axis, so if you try and stretch something that's right on the x-axis, it's not going to move anywhere. That's why it always stays where it is. So normally on x squared, we go 1 across each way and 1 up, but because it's half, we go 1 across each way and only a half up. And instead of 2 across each way and 4 up, we go 2 across each way and half of 4 up. And we saw that we got a wider parabola. So again, just like I said, after the stretches took place from x squared, the new points are what we call image points. Okay. They kept their x coordinates, but their y coordinates changed. Okay. In 2x squared, they doubled. So each value was twice the y value in x squared. Something new this year, we're going to call this a vertical stretch by a factor of 2. Factor really implies multiplication. So when you say that a stretch, there's a vertical stretch by a factor of 2, all the y's are getting multiplied by 2. And then in a half x squared, each y value was half the corresponding y value in x squared. The x value stayed the same, so we call this a vertical stretch by a factor of 1/2, because all the y values are being multiplied by 1/2. What happened here? Why it keeps just popping in these sort of lines when I change colors. We don't need to write these points. You can see the points on the graph. Okay? But I do want to write what the mapping notation would be. Remember, mapping notation is a formula for all the new points in a transform function. So for 2x squared, remember we said all the x values stay the same, so they don't move, but all the y values double. So we take every y coordinate and times it by 2. Similarly, in 1/2x squared, all the x coordinates stayed the same, but all the y coordinates, we took half of the original ones, or times it by 1/2. So just the first one became -2, +2, and -2, sorry, -2, 8. Next up, -2, 4, and so on. So whenever you do a vertical stretch of a function, okay, it doesn't have to be x squared. It could be any shape of function. Could be an absolute value function, okay? Could be a funky looking function. When you do a vertical stretch, you multiply all the y coordinates by whatever the number is in front of the function. Okay? Something that we didn't talk about last year, when you transform a function, some points will not move. They'll stay where they are. Okay? So we saw that on the previous page, what point didn't change? The origin, or 0, 0. When they don't change, we call them invariant points. So in y equals 2x squared and y equals 1/2 x squared, in both of those, zero, 0 is an invariant point. All the other ones change. Okay, just as another example, here we have another function that is in the shape of a W. I don't know what its equation is, so we'll just call it f of x. All I do know is that I am asked to take this function, f of x, and stretch it vertically by a factor of 2. Then I'm asked to stretch it vertically by a factor of 1/2. Now remember, I said there's two ways that you can do these. You can either just do it right on the graph and kind of do everything in your head. Or if it gets complicated, you can use that mapping notation where you find a formula for the new points. This one I think is pretty straightforward because there's only one thing going on. So if we look at A, it's already bad. Oh yeah. Over here too. Okay. So for A, we're going to take every point and stretch it by a factor of 2. Well, you can see that you're given 5 sort of reference points on this W. Here, 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 here. So let's take each one and double the y coordinates. So what's the y coordinate here? 4. Its new y coordinate would be 8. Here, the y coordinate is, and if we double it, it stays exactly where it is. Where does this one go? Up to 0, 4. This one stays where it is, and this one up to 8. So we can see here's our new W stretch. So that's 8. In B, we're asked to do a stretch again, but this time by 1/2. So we got to take all the y coordinates of the points that we know on the red graph and take half of the y coordinates. So this y coordinate is 4. Its new one would be 2. New one would be 2. Y is 0. New one stays where it is. Y is 2. New one goes to 1. This one stays where it is. Half of 0 is still 0. And this is 4. Half of 4 is 2. So we can see that's taking f of x, the red w, and stretching it by a factor of 1/2. It kind of compresses or flattens where a stretches out. Any questions so far? What would be the invariants for both of them? What points didn't move? Not 0, 2. 2, 0. And was there another one? Negative 2, 0. Yeah. So 2, 0 and negative 2, 0 are invariant points. This next one has more than one name taking place. So when you start tackling these, you want to ask yourself when you look at the equation, what kind of transformations are taking place, and are they vertical or horizontal? So when I look at this one, I see a number in front of the function. That tells me it's going to be a vertical stretch by a factor of 2/3. What does the 2 at the end time? It's going to move, I can't hear it, move 2 up. Now this might be a little bit complicated to do in your head, more complicated. I mean, it's possible, but you could take all the points here, here, you could even take the origin here and here, and do the new points in your head. You'd have to take 2/3 of the y and then add 2, okay? But I'm going to use the mapping notation. I'm going to create a formula for all the new points, and then I'm just going to plot those points. Well, everything happening, every transformation happening is vertical. And remember, think of an XY axis. The y-axis is vertical. The x-axis is horizontal. So if everything's happening that's vertical, it's all affecting the y's. Therefore, the x's will not be affected at all. Because we're not moving left, right. We're not doing a horizontal stretch yet. It's the y's. What are we doing to each y coordinate on the original? Multiplying by 2/3 and then adding 2. So I've got to take 2/3 of whatever the y coordinate is plus 2. So now I'm going to get all my new or image points. Remember, the x's don't change. So I can just rewrite the x's. But now I've got to calculate the new y's according to my mapping notation formula. So 2/3 of 0 plus 2. 2/3 of -3, -2, right? Because 1/3 of -3 is -1. 2/3 is -2 plus 2. Well, this is the same as this, so it's 2. And actually, so it's this one down here is the y. Those are all 2 because I've already calculated it. 2/3 of 3 plus 2. There's all our new points. Notice that when I listed all of the reference points on the original function, I always went from the left side of the graph to the right side of the graph. I do that just to make sure that I'm graphing correctly. I would suggest that when you start graphing the new points, the image points, connect as you go. If you put in all the points and then try to draw the graph, you may get a little confused. So -4, 2. -2, 0. Connect. 0, 2. Connect. 2, 4. Connect. 4, 2. Connect. And there we have our transform graph by taking 2/3 of the y's and then adding 2 to the y's. Okay. This next part is new because we didn't do it last year. Horizontal stretches. This is a little hard to wrap your head around at first, but you'll get it. Because remember when we did horizontal shifts, if the equation had minus in it, we moved it right. And if the equation had plus in it, we moved it left. So it was kind of like you're thinking opposite. It's kind of that way with horizontal stretches. Well, vertical stretches affect the y's. Horizontal stretches affect the x's. So like an accordion. So let's go back to y equals x squared and these horizontal stretches. So this is y equals x squared. Now notice the difference here. The 2 in the vertical stretch, there was no parentheses. The 2 was before the x squared. But here, the 2 is with the x squared in parentheses. So in the previous one, we always did x squared and then times 2. This one, we do times 2 and then square it because of those parentheses. Same with the half x squared. So let's just sort of do a table of values in our, well, we don't. Okay. We use table of values below. Well, I'm not red. So remember, the y values are going to stay the same, the x values are going to change. Well, when x is 0, 2 times 0 is 0, and 0 squared is 0. So when in x squared, when the point is 0, 0, when we stretch it towards, they still 0, 0. Now, 1. I don't go 1 squared times 2, I go 2 times 1 and then square it. Right? So when I plug 1 in, I need 2 times 1 is 2, squared is 4. So 1 is 4. Negative 1 is also 4, because 2 times negative 1 is negative 2, and negative 2 all squared is 4. So when I kept the y's the same, y equals 1, what happened to the x's? Yeah. So here, remember, we want to keep, like, what was it? What was the y towards the 4 on 2x squared? It was at negative 1, 4 and positive 1, 4. Remember, I'm writing the points so that the y coordinates match up, because it's the x's that are changing. Well, what about these on the original? Well, if you look at these on the original, the new ones would actually be here. So when y stayed at 1, x actually moved into 1/2. And when y stayed at negative 1, x moved to negative 1/2. Right, keeping the y's the same. So that's what happened in the new ones. Notice the y's are all the same. What happened to the x's from x squared to, in parentheses, 2x squared? They halved. So I kept the y values the same, but the x values halved. So when the 2 was inside, the actual stretch was 1/2. What do you think the actual stretch will be here? 2. Because what do? You take the reciprocal. 2 over 1, flip it, you get a stretch of 1/2. 1/2, flip it, you get a stretch of 2 over 1 or 2. Good. And we'll see that actually works. So if we do this, and I'll do this in green, we think that the x's are going to double, the y's are going to stay the same. Therefore, this point will be negative 4, 4. This point will be negative 2, 1. This stays as 0, 0. This becomes 2, 1. And this becomes 4, 4. So when we take those points and plot them up here, we can see that they're going to match up to the stretch. So in a 1/2 x, we've got 0, 0, 2, 1, negative 2, 1, 4, 4, and negative 4, 4. squared, and the red one was, sorry, not x into x squared. And then this one was y equals 2x. And that makes sense, because notice, these are the y values in the original, the red ones. The y values stayed the same in the stretch of 1/2, which is actually a stretch of 2. Okay, in the equation, it's 1/2, but when we do it on the graph, it's 2. So you've got to think about it when you get an equation where you're going to do a horizontal stretch. When you pull that number out that's in front of the x inside the function, you got to flip it to get the right stretch. So with 2x squared, each x value was 1/2. Therefore, we call it a horizontal stretch by a factor of 1/2. And in 1/2 x squared, each x value is the reciprocal of 1/2 multiplied by, or twice, which is a horizontal stretch of 2. It's kind of like when things go on horizontally, it's like reverse world. Like when you do shifts, if it's plus, you go left. If it's minus, you go right. When you do stretches, if it's 2, you multiply by 1/2. If it's 1/2, you multiply by 2, 7. Okay. Oh, I didn't ask, but just out of curiosity. What were the invariant points? Yeah, 0, 0 again. Those were the only ones that didn't move. Just something to be aware of. So now let's go back and see what happens with this W again. But now, notice where the 2 is. The 2 is not in front of the f. The 2 is inside the function. That means horizontal when it's inside. Okay? So that means that this will be a horizontal stretch of the reciprocal of 2, or 1/2. This will be a horizontal stretch of the reciprocal of 1/2, which is 2. So that means every x value gets multiplied by 1/2. Every x value gets multiplied by 2. Okay, think all that. Every x times 2. Every x So I didn't give you room for mapping notation, but you could always use mapping notation here. Okay, when we do y equals f of 2x, the mapping notation formula would be every x gets multiplied by 1/2, every y stays the same. So it'd be 1/2 x comma y. This one, every x gets multiplied by 2, every y stays the same, so it's 2x comma y. But we can do it directly on the graph. So remember, we're changing the x's now. So what's the x coordinate here? Careful. -4. Okay, so I'm going to multiply -4 by 1/2. -2. Remember, the 4 stays the same. So it goes from -4 to -2, 4 stays the same. This one, the x is -2. The new x, -2, 0. The new x will be half of -2, -1, 6. This one, the x is 0. Half of 0 is still 0. This one, the x is 2, the y is 0. Half of x is 2. And here, the x is 4, the y is 4. So we take half of x2, and the y stays at 4. So we see, we get that. So again, it's kind of reverse world happening here. You think with 2, a horizontal stretch of 2, it would go out. No, it actually stretches in or compresses. And we saw that on the previous page. And then for B, we go back to the red graph, take those reference points, and then do half of every x, keep the y's the same. Sorry, double every x, keep the y's the same. So x is 4 here, the new x will be 8, 4. Sorry, x is -4, it'll be -8. Here x is -2, the new x will be -4, and y stays the same. Here, x is 0, 2. New one would be 0, 2. 2 times 0 is 0, and 2 stays as 2. This one, x is 2, therefore its new x will be 4. That as I go. And this one, x is 4, its new x will be 8, 12, 4 stays the same. So that's really the new thing with stretches, is the horizontal. Okay. What about if we work backwards? And this is, like I said yesterday, there's 2 big things when we do transformations. One, you're given a graph, you're asked to transform it a certain way, and you draw the new graph. The second big type is you're given the graphs of the new and the original, and you're asked to figure out the equation, like this. Okay? So we've got f of x and g of x. So you got to think of, so we are asked here, state g of x, the new one, in terms of f of x, the original. Okay, so think of g is new, f is the original. So the red is the original, the g is what happened when we transformed it. And clearly there's no vertical stretch going on. There's no shifting going on. It's being stretched horizontally, it's actually being compressed in. So by how much? By what factor? Well, what's the x coordinate of this point? 6. What's the x coordinate of the new point? What do I multiply to get from 6 to 2? 1 over 3. When you go smaller, you always multiply by 1 over 6 divided 2. So that means that the stretch is 1/3. Okay, the stretch is 1/3. But when I put it in the equation, I don't write 1/3. I got to flip it and make 3. So this one will actually be f of 3 of x. Yeah. Yes, it would be, because that's a vertical stretch now. Yeah. How about if we reverse them? We say that G is the original, the blue is the original, F is the new. What do we multiply to get from here to here? X's? 3, but in the equation it goes 1 over 3. Now you're getting it. So weird things happen horizontally. Normal things happen vertically. What were the invariant points for both of these?
0,
0, 4. Those are the ones that didn't move. All these other ones out here, the upside down D, they moved. But 0, 4 stayed exactly once. Okay. So just a quick sum, like I did with the shifts or translations. If there is a number being multiplied in front of the function, that is a vertical stretch. If there is a number inside the function being multiplied by x, that is a horizontal stretch. And in a vertical stretch, whatever that number is in front, that's what we multiply the y coordinates by. So there's a vertical stretch by a factor of a. And it should be absolute value of it, because negative means another transformation that we'll talk about next week. But if it's a horizontal stretch, that numbers that is in front of the x being multiplied by the x that's inside the function, there's a horizontal stretch by you got to take the reciprocal of b. So you got to flip b. Factor of 1 over, and b is going to be positive, so we put absolute value bars around it. So now we've got, you don't have to write this. So now we've got functions that could look like this. Notice the letters we use. In 1.2, we talked about these two, horizontal shift, vertical shift. In this lesson, we talked about these two, vertical stretch, horizontal stretch. Okay, so notice that whenever, like I said before, if it's inside the function, okay, so notice I put brackets around everything inside F. That's all horizontal. That's all X. If it's outside the function, here and here, it's vertical. The last thing we have to do is what happens if we have negatives in front here. And I think you know. But we'll talk about that next week. Okay. So this is probably the most challenging of the 3 transformations. Just because, especially that horizontal one, you got to remember. But you'll get it. Okay.